Hello everyone. Welcome to our presentation. Today, we'll be exploring the topic of math's NCERT surface area and volume. This is a fundamental part of geometry that helps us understand the properties of different shapes. In this session, we'll cover the key concepts, formulas, and methods to find surface areas and volumes of various solids. I'm excited to guide you through this topic, so let's get started. All right, let's take a quick look at what we'll be covering today. On this slide, we have the contents of our presentation, starting with the cube. We'll then move on to the cuboid, and later we'll explore the volume of different shapes. You'll notice we also have specific focus on the sphere, the right circular cone, and the hemisphere. Additionally, we'll discuss surface area, particularly the lateral surface area, which is crucial in understanding how much material covers these shapes. Towards the end, we'll tie everything together with a comprehensive conclusion. This outline is designed to guide us through the key concepts of three-dimensional shapes, their properties, and how we calculate their volume and surface area. So, let's dive in and explore these shapes one by one, seeing how they fit into the bigger picture of geometry and real-world applications. Let's take a closer look at the cube. A cube is a fascinating shape because of its symmetry and structure. It's a three-dimensional object, which means it has length, width, and height. You can think of it as either solid or hollow, depending on its purpose or design. The defining feature of a cube is that it's contained by 6 equal squares. These 6 faces are all identical, making the cube perfectly symmetrical from every angle. This symmetry is what makes the cube such a fundamental shape in geometry and design. Understanding the properties of a cube helps us see how basic shapes come together to form more complex structures, which ties back to our overall theme of exploring geometric forms and their applications. Let's take a closer look at the surface area of a cube. If we imagine the cube template, it's quite straightforward to see that it has 6 sides, and each side is a perfect square. Now, the area of one of these squares is simply side length A multiplied by itself, which we write as a squared, or A2. Since all 6 sides are identical squares, to find the total surface area, we just need to multiply the area of one side by 6. That gives us the formula. The total surface area, or SA, equals 6 times a squared. This is a fundamental concept because understanding how to calculate the surface area helps us grasp how much material is needed to cover the entire surface of the cube, tying into our overall theme of understanding geometric measurements. Let's talk about the volume of a cube. The volume is basically how much space the cube takes up. To find it, we multiply its length, width, and height together. That gives us the formula. Volume equals length times width times height. Now, in a cube, the interesting thing is that all 3 dimensions, length, width, and height, are the same. So, instead of multiplying 3 different numbers, we can simplify the formula to just 1. This is where the shortcut comes in. The volume of a cube is just the length of one edge raised to the 3rd power. We write it as V equals S cubed, or S to the power of 3. Remember, S represents any edge of the cube, since all edges are equal. This formula makes calculating the volume quick and easy once you know the length of one side. It connects to the overall theme of understanding shapes and their properties, helping us see how dimensions relate to space. Let's take a closer look at a cuboid. A cuboid is essentially a box-shaped solid object, which you might be familiar with from everyday life. It has 6 flat sides, and what's interesting is that all of its angles are right angles, meaning they measure 90 degrees. This gives it a very regular, structured appearance. Additionally, every face of a cuboid is a rectangle. This uniformity in shape and angles makes the cuboid a fundamental shape in understanding 3-dimensional geometry, especially as we look at different solid figures and their properties. Recognizing these key features helps us analyze and identify cuboids easily in real-world objects, and it ties into our broader exploration of geometric shapes and how they relate to the objects around us. Let's now look at how to calculate the surface area of a cuboid. To do this, we need to find the area of each face and then add all those areas together. First, consider the top and bottom surfaces. They each have an area of length times width, which is written as 2LW because there are 2 such surfaces. Next, the two side surfaces. These are the faces that run along width and height, so their combined area is 2WH. Then we have the front and back surfaces, which are determined by length and height, giving us 2LH. When we add all these areas together, we get the total surface area of the cuboid. Mathematically, it's expressed as 2LW plus LH plus WH. This formula is really useful because it sums up the areas of all the faces in a simple way, giving us a complete picture of the total surface area. Remember, understanding how each part contributes helps us see the bigger picture of the shape's surface. Let's take a look at this shape. When we're talking about volume, there are 3 key measurements we need to consider: length, width, and height. These measurements help us understand how much space the shape occupies. To find the volume, we use a simple formula. Volume equals length times width times height. You might see it written as V equals L times W times H, which is just a shorter way of saying it. And for even easier reference, we often write it as V equals LWH. Understanding this formula is really important because it connects directly to how we measure the space inside three-dimensional objects. It's a fundamental concept that ties into the overall theme of understanding shape and size in our world. So, whenever you're asked to find the volume, remember, it's just length times width times height, simple and straightforward. Now, let's take a closer look at the cylinder. A cylinder is a solid object that has 2 identical flat ends, which can be either circular or elliptical in shape. These ends are parallel to each other and serve as the top and bottom surfaces of the cylinder. Connecting these 2 ends is a curved side, which wraps around the entire shape. This curved surface is what gives the cylinder its distinctive round, tube-like appearance. Understanding these key features helps us recognize cylinders in both everyday objects and more complex structures. As we continue exploring different solid shapes, keep in mind how these characteristics define a cylinder's unique form and how they relate to the overall theme of geometric solids. Now let's talk about the surface area of the lateral, or curved, surface of a cone. The key formula here is lateral surface area, which is given by 2 pi RH. This might look a bit complex at first, but let me break it down. The R represents the radius of the cone's base, which is the distance from the center to the edge. Pi, of course, is the mathematical constant approximately equal to 3.14, and H is the height of the cone, measured from the base to the tip. What's important to remember is that this formula helps us find the area of the cone's curved surface that wraps around the inside. It's different from the total surface area because it doesn't include the base itself, just the side surface. Understanding this is crucial because it connects directly to how we calculate the surface area of three-dimensional shapes, which is a key part of understanding their properties. Whether you're working in engineering, design, or even everyday problem solving, knowing how to find the lateral surface area gives you a powerful tool for analyzing these shapes. Let's take a closer look at the surface area, specifically the total surface area of a cylinder. The surface area actually has a few different parts to consider. First, we have the surface area of both ends of the cylinder, which is calculated as 2 times pi times the radius squared. This accounts for the top and bottom circular surfaces. Next, we look at the surface area of the side, which is essentially the curved part that wraps around the cylinder. To find this, we use 2 pi times the radius times the height. Finally, if we want to put everything together to get the total surface area, we combine these parts. The complete formula becomes 2 pi r times the sum of the radius and the height, which simplifies to 2 pi r times the quantity r plus h. This total surface area formula is really useful because it gives us a comprehensive way to measure how much material is needed to cover the entire surface of the cylinder. Remember, understanding each part helps us see how these formulas come together in practical applications. Now, let's talk about how to find the volume of a cylinder. To do this, we multiply the area of the base by the height of the cylinder. The area of the base is calculated using the formula pi r2, where r is the radius of the circle at the bottom. Once we have that, the volume is given by multiplying pi r2 by the height, which we usually denote as h. So, The formula for the volume looks like this. Volume equals pi r 2h. Sometimes you'll see it written simply as volume equals pi r 2h again, emphasizing the key components. Remember, the height h is the distance from the base to the top of the cylinder. This calculation is crucial because it helps us understand how much space the cylinder occupies, which ties back to our overall theme of understanding geometric measurements. So, in essence, volume is just the base area times the height, giving us a clear way to quantify three-dimensional objects like cylinders. Let's take a closer look at the right circular cone. A cone, in general, is a three-dimensional shape, and when we specify a right circular cone, we're talking about a particular type. The key feature here is that its surface is generated by lines, or generatrices, that join a fixed point, called the apex, to every point on a circle. Now, what's special about this fixed point? It's located on a perpendicular line that passes through the center of the circle. This means that the apex is directly above the center of the base circle, forming a perfect right angle with the base. This configuration ensures that the cone is symmetrical, which is why we call it a right cone. The importance of understanding this shape lies in its symmetry and how its surface is formed by those lines connecting the apex to the base. In the context of our overall themes, recognizing the unique properties of the right circular cone helps us understand more complex geometric structures and their applications, especially in fields like engineering and design. So, grasping this fundamental shape sets the foundation for more advanced concepts ahead. Let's talk about the slant height of a right circular cone. To find it, we use Pythagoras' theorem, which is really handy for right-angled triangles. In this case, imagine the cone's height and radius forming a right triangle with the slant height. So the formula is a 2 plus b2 equals c2. Here, b represents the height of the cone, which we denote as h, and a is the radius. The slant height, which we'll call L, is what we're trying to find. Applying Pythagoras' theorem, we get that L equals the square root of h squared plus r squared. This means that to find the slant height, we take the square root of the sum of the squares of the height and the radius. This concept is important because understanding the slant height helps us determine the surface area of the cone and other related measurements. It ties back to our overall theme of understanding the key dimensions of three-dimensional shapes. Now let's take a closer look at the lateral surface area of a cone. This is the area of the curved surface that wraps around the cone, excluding the base. The formula for calculating this lateral surface area is quite straightforward. It's pi times the radius times the slant height. So, when you see the formula written as lateral surface area equals pi rl, remember that r is the radius of the base, and l is the slant height, which is the length from the apex of the cone down to the edge of the base along the surface. This measurement is important because it helps us understand how much material is needed to cover the sides of a cone, which can be useful in various real-world applications. Connecting this to our overall theme, understanding the surface areas of different shapes allows us to solve practical problems involving materials, design, and space. So when we talk about the surface area of a cone, we're essentially looking at two parts: the area of the base, which is a circle, and the area of the cone's curved surface itself. The total surface area is then the sum of these two parts. The formula we use is surface area, or SA, which equals pi times the radius squared, plus pi times the radius times the slant height. Now, to clarify the variables, r is the radius of the base, and L is the slant height, which is the length from the tip of the cone down to the edge of the base along the surface. This formula is really useful because it helps us quickly find the total area that the cone's surface covers, whether we're thinking about wrapping it, painting it, or just understanding its size. Remember, the key is understanding how the base area and the curved surface area come together to give us the total surface area. Now let's take a closer look at the volume formulas for cylinders and cones. As you can see on the slide, the volume of a cylinder is given by pi times the radius squared times the height, which is written as pi r 2h. This formula essentially tells us how much space is inside a cylinder. Similarly, for a cone, the volume formula is 1/3 of that of a cylinder, or 1/3 of pi r 2h. This makes sense because a cone tapers to a point, so it occupies less space than a cylinder with the same base and height. The key point here is that both formulas involve the same base area, pi r 2, and the same height. H. The main difference is the factor of 1/3 for the cone. Connecting this to our overall theme, understanding these volume relationships helps us see how different shapes relate to each other. The cone's volume being 1/3 of the cylinder's is a fundamental concept that appears in various applications, from geometry to real-world engineering problems. So remember, when calculating the volume of a cone, you can think of it as a scaled-down version of a cylinder, precisely 1/3 as large. Today, I want to talk about the sphere. A sphere is a perfectly round, solid figure, kind of like a ball. The key thing to remember is that every point on its surface is exactly the same distance from the center. This distance is called the radius. Think of a basketball or a globe. Both are good examples of spheres. The concept of a sphere is fundamental in understanding three-dimensional shapes because of its symmetry and uniform surface. When we explore different geometric shapes, the sphere stands out due to its unique properties. It's a perfect example of how uniformity and symmetry come together in geometry, which ties into our overall theme of understanding the natural and mathematical world around us. Let's talk about the surface area of a sphere. The key formula to remember here is that the surface area, which is essentially the total area covered by the outer surface of the sphere, is given by 4 times pi times r squared. Now, r represents the radius of the sphere, which is the distance from the center to any point on the surface. This formula is important because it helps us understand how the size of the sphere's surface changes as the radius increases. As you can see, the surface area grows proportionally to the square of the radius. This concept connects to our overall theme of understanding geometric properties and how they relate to real-world objects. So, whenever you're working with spheres, just remember this formula and how the radius influences the surface area. Now, let's talk about the volume of a sphere. The volume is essentially the amount of space that the sphere occupies. The formula for calculating this volume is 4/3 times pi times the radius cubed. This means that as the radius increases, the volume grows quite rapidly, since it depends on the cube of the radius. The key point here is that the radius, which is the distance from the center to any point on the surface, plays a crucial role in determining the size of the sphere's volume. Understanding this formula helps us see how changing the radius impacts the overall volume, which ties back to our broader theme of understanding three-dimensional shapes and their properties. Today, I want to talk about the concept of a hemisphere in geometry. A hemisphere is essentially an exact half of a sphere. Imagine taking a sphere, like a globe, and slicing it right through the middle. What you get on one side of that cut is a hemisphere. It's a very precise division, meaning each hemisphere is exactly half of the entire sphere. This idea is important because it helps us understand how spheres can be split and analyzed in geometry. Throughout this presentation, we've been exploring different parts of three-dimensional shapes, and the hemisphere is a key example of how symmetry and division work in these forms. So, in summary, a hemisphere is simply one half of a sphere, created by slicing it through its center, and understanding this helps us grasp more complex geometric concepts. All right, let's take a closer look at the surface area of a hemisphere, specifically the lateral surface area. The formula for this is 2 pi r squared, where r is the radius of the hemisphere. What this means is that if you know the radius, you can easily calculate the curved surface area that wraps around the hemisphere. This is an important concept because understanding the surface area helps us in various real-world applications, like calculating material needed for hemispherical objects or understanding their properties better. Remember, the key here is that we're only talking about the lateral surface area, not the total surface area, which would also include the base. So, in summary, the lateral surface area of a hemisphere is given by 2 pi r squared, and this formula is a handy tool in geometry and beyond. Let's take a closer look at the surface area of a hemisphere. We know that the area of a circle with radius r is pi r2, which is a fundamental concept here. Now, when we consider a hemisphere that includes its base, the total surface area is a combination of two parts. First, the curved surface area, which is 2 pi r2, and second, the area of the base itself, which is pi r2. When we add these together, the total surface area becomes 3 pi r2. This is an important point, because it shows how the surface area of a hemisphere isn't just about the curved part. The base contributes as well when it's included. Understanding this helps us better grasp the geometrical properties of hemispheres, especially when calculating surface areas in real-world applications. It ties back to our overall theme of understanding the relationships between different parts of three-dimensional shapes. Now, let's talk about the volume of a hemisphere. The key point here is that the volume of a hemisphere is exactly half of the volume of a sphere. So, if you know the volume of a sphere, you can easily find the volume of a hemisphere by dividing that by 2. The formula for the volume of a hemisphere is V equals 2/3 pi times r cubed, or in symbols, V equals 2/3 pi r cubed. This formula makes sense because it's just half of the sphere's volume, which is 4/3 pi r cubed. Understanding this relationship helps us see how the geometry of a hemisphere relates to that of a sphere, which is a theme running throughout this presentation. It's a neat way to connect different shapes and their properties, emphasizing how formulas are connected and how we can manipulate them to find what we need.